Refraction video number 4 is here. And I'm reminded of this picture over here, and we're imagining this time that we're going from air, medium 1, into glass, medium 2, which is often the case. And the first thing I'm going to do is show you a simplification of Snell's law, which we often find in textbooks. So this is the way that it has been presented to you. Sine theta 1, n1 sine theta 1 equals n2 sine theta 2. And if we start with air, for air, n1 equals 1. So if n1 equals 1, 1 times sine theta 1 is just sine theta 1. So therefore, this simplifies to sine theta 1 equals n2 sine theta 2. And then we can divide both sides by sine theta 2. If we divide both sides by sine theta 2, then we get n2 equals sine theta 1 over sine theta 2. Now, this is how you often see the formula in textbooks. It just says n, and it says sine I, sine r. And what it's assuming is that this angle here, theta 1, is angle I, and this angle theta 2 is angle r. And I stands for angle of incidence, and r stands for angle of refraction. But hang on a minute. Didn't we just say that the path is the same even if it's coming the other way? So in which case, should we swap I and R? How does that work? And it also only has one refractive index in the equation. Yeah, but that's because the other one is the refractive index of air. And the refractive index of air is 1. So N1 has disappeared. But we still like this complete form, which always works, of Snell's law. It's particularly important with optic fibers when you're considering small mediums, changes, and information going along an optic fiber. Okay, so that's the first thing I wanted to talk about. And then the second thing I wanted to talk about was the idea of dispersion. So here we go, dispersion. Dispersion is what causes rainbows, and dispersion comes about because the refractive index is not exactly constant for different colors of light. So that means that if you get white light going into glass, red light follows angle theta 2 that's slightly different from blue light. So I'm going to illustrate that with a picture of a prism. The reason I've chosen a prism, and the reason that you can see prisms in my PowerPoint presentation, is because the effect is greatly magnified with a prism. And I'll just show you why. When the light comes up to the prism like this, when it goes into the glass, it bends towards the normal. So it bends that way. But when it comes out of the glass, the other side, it bends away from the normal. So it bends even more. You see, that's because the normal is first one side and then the other side. Those aren't very good perpendiculars, but never mind. Okay, so what happens to the red and blue light? Well, here comes the red. It doesn't bend quite as much. So it goes like that, and then it goes like that. I've exaggerated it a bit. And then here comes the blue light. The blue bends best. And that's how I remember it, and that's how everybody remembers it. The blue bends more. Blue bends best. So, as a result, the colors spread out into all the colors of the rainbow.